Hi again, Somewhere here, and welcome back to Go DevOps. So if you joined us in the second episode, you now understand why containers are so lightweight compared to virtual machines. And in today's episode, we're going one step deeper. So we'll explore the internal architecture of a container, so the layers, the runtime, and how everything works together under the hood. And this is where containers start to reveal their real magic. So don't worry if it sounds technical. I'll guide you step by step with clear visual and examples. So let's go. Let's get started with this new episode. So when people hear the word container, they often imagine something heavy, like a sort of a lightweight virtual machine. But at runtime, a container is really just a regular Linux process. But what makes it special is how that process is heavily isolated from everything else. So thanks to kernel level features like namespace and cgroups, the container process doesn't see the host system, doesn't share files or process identities, so the PIDs, with others, and can be strictly limited in resources. And this is the secret behind containers being so fast, so lightweight and portable. There is no full operating system involved, just one process running inside a well-defined boundary. So the key takeaway is that a container is not a mini virtual machine. It's more like a Linux process with strong isolation boundaries. So let's break down how a running container is actually structured internally. So at the very top, we have your application, so whether it's a web server or any executable code. So that app runs inside an isolated file system. So it only sees the files that it needs, not the host file system. This isolation is created using the Linux namespace and layered file systems. So below that, there is the container runtime. It's responsible for setting up the environment, applying isolations, and managing the container lifecycle. So it works with low-level tools like runc to actually launch the container process. And finally, everything runs on the host shared Linux kernel. So unlike a virtual machine, there is no extra operating system. All containers share the same kernel, which makes them extremely efficient. And this stack is what gives containers their power, speed, isolation, and low overhead. And this isn't a full system like a virtual machine. It's just layers of abstractions around one Linux process made to feel like its own world. So let's talk about how containers isolate their view of the file system. So on the left, we see what the container sees: a minimal, clean, root directory with only its own files and maybe its application folder too. And on the right, we see what the host actually sees. So a full file system with everything, including a subdirectory like the last one, where the container's root is mounted. And this isolation is made possible by mount namespace and /root-like behavior. And these features ensure that the container cannot see or interact with files outside of its designed root. So from inside, it thinks it's running on its own machine, but it's really just operating within a restricted view. And this is a key part of a container security and portability. So it runs anywhere, but only sees what it's supposed to. And in short, the container gets its own word, but that word is just a folder carefully isolated from the rest. So Linux namespace provide virtual separation for almost every critical system resource. So they isolate process IDs. So each container has its own independent set of running processes. Networking is separated. So containers have their own network stacks and interfaces. Other namespace like UTS isolate the host name and domain name, mount namespace, control the file system views, and EPC namespace, isolate inter-process communication, and finally, user namespace provides separate user and group IDs. So together, these namespaces make your container think like it's running on its own dedicated system, fully isolated from other containers and the host itself. And now for cgroups. So when multiple containers run on the same host, resource sharing becomes a critical challenge. So this is where control groups or cgroups comes in. And it's a powerful feature built into the Linux kernel. So cgroups allow us to precisely allocate, monitor, and limit resource usage for each group of processes, which in the context of containers means each individual container. So with cgroups, we can define how much CPU, time, memory, and even bandwidth each container is allowed to consume. So for example, in here we have the container A, might be restricted to a single CPU core and 512 megabytes of RAM, while containers B is allocated 2 cores and a full gigabyte of memory. So this resource isolation ensures that no single container can overconsume and affect the stability of the system. So it guarantees predictable performance and helps enforce service-level agreements and contributes to the overall efficiency and security of containerized environments. So in short, cgroups are a fundamental part of what makes containers manageable at scale, especially in production-grade systems. So one of the most powerful aspects of container architecture is that containers do not boot their own operating system. Unlike virtual machines, containers do not include a kernel. So instead, every container on the same host shares the same Linux kernel provided by the host system. So all system calls, file operation, and networking inside a container are handled through the shared kernel, so giving the illusion of a complete system without the overhead. So in short, a container is just an isolated process, but it still fully relies on the host kernel to function. So now let's take a look at what actually runs a container. It's the container runtime. So when you launch a container using a tool like Docker, for example, Docker doesn't directly run the container itself. Instead, it hands that job off to a runtime layer beneath it. So the most common runtime used today is Containerization, and it handles the container's full life cycle from creation to execution to shutdown. And Containerization itself then uses a low-level tool called runc, and it's the component that actually creates the isolated Linux process. So applying the namespace configuration, setting up cgroups, and building the container environment. And this process doesn't run in a virtual machine. It runs directly on the host Linux kernel, just like any other system process that is only isolated. So to summarize, Docker delegates to Containerization. Containerization calls the runc, and runc creates a secure sandbox process on the host. When a container is launched, what actually starts is a regular Linux process, and this process is isolated and managed by the container runtime, which controls its environment throughout its life. So the life cycle begins with the start phase, where the runtime sets up the container namespace, mounts its isolated file systems, and applies cgroups for resource limits. Next comes the execution phase, so where the app inside the container runs just like any normal Linux process, but completely sandboxed. And throughout this phase, the runtime is actively monitoring the container, so it watches over its state, enforces restrictions, and ensures that the container stays isolated and healthy. Finally, when the container's main process ends, so whether naturally or due to a failure, the container rushes the stop phase, and at that moment, the container is terminated and cleaned up automatically. So no virtual disk to shut down, no system to reboot, just one process ending and disappearing. And this what makes containers so fast, lightweight, and disposable. Let's now look at what the application actually sees when it's running inside a container. So from its perspective, it's running on a fresh standalone system. So first, it sees itself as PD1, and the very first process, so in its own environment, and that's a strong indicator that it's isolated from all other system processes. And next, the app sees a custom hostname, something like here for the example, container 42, which is not the hostname of the host machine. And if the app lists the contents of the root file system, it finds only what's inside the container, so a minimal isolated directory structure. So it cannot see the host files, other users, or system level resources. This is made possible by Linux namespace and the environment set up by the container runtime. So in short, the app feels like it's running on its own machine, when in reality just a carefully isolated process on a shared host. So this isolation of independence is one of the key reasons why containers are so efficient and portable. So what should you take away from this video is that a container is not a tiny virtual machine. It's fundamentally a regular Linux process, but isolated using clever kernel feature. So it's used namespace to isolate key system aspects, including the file system, the process IDs, networking, user IDs, and more. And with cgroups, we can control how much CPU, memory, and bandwidth each container gets, preventing resource hogging and ensuring stability. And all containers share the same host Linux kernel, which is why they can launch quickly and use minimal resources. And behind the scene, a container runtime is like so a container runtime, like container ID or a runc, handles the life cycle from creation to shutdown, making sure everything stays isolated and managed. And in short, a container is fast, lightweight, secure unit of execution built on top of the Linux kernel, and that's what makes them so powerful in modern infrastructure. So thanks so much for watching today's video, and I hope the internal working of a running container are much more clearer now. And if this video helped you, feel free to give it a like, share it with a teammate, and subscribe so you don't miss what's coming next. So for the next episode, we'll go one level deeper and look at how containers run on a host machine. So from user space to kernel interactions. And if you're curious about anything specific or got a container concept that's still fuzzy, drop in the comments. I really read every single one of them. So yeah, thank you.